Hey guys, how are you doing? I hope that you're doing well. I miss you like crazy. So I thought that we could go ahead and do some screencastify today. So I'm going to talk to you a little bit about enthalpy, and I'm going to do a second video on thermochemical reactions. So I'm actually going to do two videos today. So right now, I'm going to talk to you a little bit about enthalpy. So enthalpy, guys, is H, also known as delta H, and it is just the amount of heat energy that's given off at a constant pressure. So enthalpy and heat are used kind of interchangeably. So a lot of times it's going to talk about how much energy or heat has been given off in a reaction or is taken in by a reaction. So let's go ahead and get started with that. So as I said before, enthalpy is the amount of heat energy that you're going to either get used up in your reaction or given off. And so you have H is the symbol for enthalpy, so that's what you'll see there. You also will have delta H of RXN. RXN is just an abbreviation for reaction, and that's the change in. So delta H, change in enthalpy. And so you do that by looking at the energy of your products minus the energy of your reactants. And a lot of times enthalpy is going to be measured in kilojoules. So that's the heat energy unit that you will be using. So delta HF, that is the heat of formation, and it's the amount of energy it takes to form 1 mole of the substance. So for example, here I have an equation. I have 2 moles of solid potassium. I have 1 mole of liquid bromine. Remember that bromine is part of Brinkelhoff. It's a diatomic. So that one is going to be Br2, and that actually occurs naturally in its liquid form. That's why it's blue on the periodic table, is because it's actually a liquid. And then that will form 2 moles of potassium bromide, KBr, which is also a solid. And so it's telling me that potassium, 2 moles of potassium, and 1 mole of bromine is going to require energy to form the 2 moles of potassium bromide. So the enthalpy, the delta H, is talking specifically in this case about the delta HF, the heat of formation. So it's going to how much energy it actually takes in order to create that reaction. So there are a lot of different charts that actually give you your delta HF values. There are set values for the heats of formation for many substances. We have one on page 975 in our textbook, but if you Google heat of formation values, you'll be able to find a lot of stuff online as well. So the heat of formation is going to be 0 for any substance in its naturally occurring form. So you're looking at all your diatomics, so Brinkelhoff, so oxygen and hydrogen, for example, those gas forms. Any of your metals, solid, magnesium, for example, those are all naturally occurring. They're already formed, so you don't have to put any heat energy in, or you don't have to take any heat energy out. So because of that, it's going to be a 0. So I'm going to show you, this is an example of a chart here. And let's just look at the first couple, for example. So you'll see solid silver right here. The delta HF, heat of formation, is 0. And again, because that one is a already formed substance, there's nothing that's put in or taken out in order to have 1 mole of it. But if you look down here, AgCl, okay, this is silver chloride. Now you'll notice that it's going to take negative 127.068 kilojoules to form 1 mole. And it's actually giving off that amount. So when this is formed, it gives off this specific amount of heat. But if we look at silver cyanide, now you see a positive number, 146, and that's how much energy is actually going to be input to form 1 mole. So keep in mind that positive and negatives here are going to be something that you want to pay attention. So the negative value is how much heat is given off, whereas any positive number you have is going to be how much is put in to form that 1 mole of substance. Now, there's one other thing I want to mention to you. Pay attention to how your states of matter are given to you in your equation. So if you look at water, for example, water has different values depending on if it's a liquid or if it is a gas. So that's one thing that you're going to want to pay attention to when you're given an equation is what form is your reactants or your products in, because that form can actually dictate what your heat of formation for this is. So just kind of keep that in mind as you're going through. Okay, so what you're going to do is you're going to use this equation right here in order to determine how much heat is either being given off or being taken in. So here's the heat of reaction. Remember that RxN means reaction, and this is a sigma, and sigma means sum, S-U-M. So you have the sum of the heat of formation for your products minus the sum, S-U-M, of the heat of formation for your reactants. So in order to do this, you have to have that chart. So you will need to look at your values either from online or from your book, because you won't be able to do that without these. So, but those are the values from that chart that it's going to take to form 1 mole of that substance, and it's either going to give off that amount of heat energy or it's going to put in that amount of heat energy. Okay. The other thing that you want to pay attention to, guys, is also you need to have a balanced equation. So because of that, they're not all going to be 1. So for example, here's my reaction. These are not all 1s as my coefficient. I have a 4, I have a 5, I have a 4, and I have a 6. So when you're looking up your delta HF, your heat of formations, you need to make sure that you multiply by the number of moles from your balanced equation. So do a quick check. Is your equation balanced? If it's not, do that, because that will also dictate your final answer for this. So you're going to take your heat of reaction by looking at these values, plugging it into this equation, and then we're going to go from here. So let me show you an example here. So here's the equation I just shown you. I have 4 moles of ammonia in its gas form, plus 5 moles of oxygen in its gas form. Those react to give me 4 moles of NO in its gas form, plus 6 moles of H2O in its gas form. So again, all of these are going to be in gas form. So pay attention to that, especially water, when you are looking up your values. So you have these values come right from the chart. So step 1, you're just going to look up what each of these are. So there is only 1 in its natural form. So O2 is going to be 0. So everything else you're going to want to look up. So ammonia is going to be negative 45.9 kilojoules. I already mentioned oxygen is 0. NO is going to be 91.3 kilojoules. And then H2O is going to be negative 241.8 kilojoules. So what you're going to do is you're going to plug this in to your equation. So remember, it's the sum of the products minus the sum of the reactants. A lot of people flip that because your reactants come first in an equation, but keep in mind that this is actually sum of products first. So you want the stuff that's on the right-hand side of your equation to come first, minus the side for your reactant side. And again, just another note that you want to make sure that you multiply by the coefficients, the number of moles in front. So for example, for NH3, that value is negative 45.9. So when I plug that into my equation, I'm going to take that and I'm going to multiply it by 4, okay, and so on and so forth. So I will show you what that looks like right here. So sum of products. So my products in this equation are nitrogen oxide and water. So we're going to put those first, okay? So here you can see I just multiplied 4, because that's the number in front, times 91.3 kilojoules. That was my delta formation of NO, plus 6 moles of water. So 6 times the heat of formation value for water, which is negative 241.8 kilojoules. So you're going to multiply these together and then add them. Again, that's your product side. and then you're going to subtract your reactant side. So I only have one reactant because if you remember from the equation, this is 0 because it's in its natural form. So really, I only have one reactant with a number here. So I'm going to take 4 times negative 45.9 kilojoules, and then my 0 for my oxygen. So when you do that, you're going to get this side is negative 1085.6, and this side is negative 183.6. So you have negative 1085.6 minus negative 183.6, and your final answer is negative 902 kilojoules. So because this is a negative value, that is how much heat was given off in that reaction. So because it's negative, it's how much heat was released. So in this reaction, negative 902 kilojoules was given off in order to form our products. Okay? All right, let me show you another example here. Okay, calculate the heat of reaction for the following reaction. So here's my reaction. I have 2 moles of nitrogen oxide again in gas form, plus oxygen, 1 mole of oxygen in its gas form, and that gives me 2 moles of nitrogen dioxide in its gas form. So same as last time, you're going to take your chart and you're going to look at your values here. So NO, we already used on that last equation, so we know that that one's 91.3 kilojoules. Oxygen, again, because it's in its natural form, is 0. And then NO2, based on that chart, is negative 33, oh, I'm sorry, not negative, just 33.2. So when you go through this now, you're going to plug in products minus reactants. So your nitrogen dioxide is going to go first. So you're going to plug in 2. Remember, there's that 2 in front of that product there. So you want to multiply 2 times 33.2 kilojoules. Subtract that from now your sum of your reactant side. So I have 2NO, so 2 times 91.3, and then again 0 from my oxygen. So in this case, when you multiply and then subtract, you get negative 116.2 kilojoules. So negative 116.2, so it's negative. So that's how much heat was released when nitrogen oxide and oxygen were forming nitrogen dioxide. So that's what you're calculating, how much heat in this case was released because it is a negative number. Okay. One variation I want to mention to you really quickly is, for example, if you're given your heat of reaction, so in this case, I'm actually given negative 91.7 kilojoules. So here's my reaction. And it's actually asking, based on my heat of reaction and then based off of the others, what's my heat of formation for FeO? So you are going to still plug in same equation you did last time, products minus reactants. So my products are iron, which is going to be 0 because it's in its solid form. So I would have to look up carbon dioxide gas, and I would plug that in to my product side. So for that one, I would only really have one number because iron would be 0. Then I would look up the value for carbon monoxide, okay, in gas form. So that would be my second reactant, but FeO, this is actually what I'm trying to solve for. So I know my products minus, I know one of my reactants, and because I know my heat of reaction here, my total, you can take, and it's just going to essentially be an algebra problem. I would take whatever number is here minus whatever number is here, but also FeO, because that's the one I'm looking for, that would be considered my X. There are 2 of those though, so you would want to account for that. So this is actually 2X. So you would have just an algebra equation with 2X on the left-hand side, solve for X, and then you would be able to find out what FeO's value is. So that is just a variation that you might see. And as long as you're given your delta H, your reaction, your heat of reaction, then you should be able to solve that no problem. So this was on how to calculate heat of reaction using heat of formation. So just keep in mind, heat of reactions, how much heat's either being input or being given off when you're actually forming moles of substances. So thanks for listening, and I will talk to you guys later. Bye.